Okay, guys, so we are going to talk about Hess's Law. And so let me kind of give you a definition of Hess's Law first. Hess's Law states that the change of enthalpy depends on the initial state and the final state and not the pathway. So the pathway to get to the final products is irrelevant in regards to enthalpy. That's what Hess's Law states. So let me kind of give you a physics analogy to help you understand what this means. So let's say that this is your home, and this is your friend's house, and this is your school. If you walk from your home to your school, well, there is a displacement. There is a distance between your home and your school, and that is displacement. But if you walked from your home to your friend and then to school, the displacement distance, the displacement was the same. It did not matter if you went straight to the school or if you went to your friend's house first and to school. Your displacement is the same. Now, your distance traveled is not the same, but in this case, in this physics analogy, displacement would be analogous to Hess's law. It doesn't matter how you got there. The distance from home to school, from your starting point to your ending point, is the same. It doesn't matter if we went by that path or by this path. This distance is the same. And so that's kind of an analogy with Hess's law. And so Hess's law is what's called a state function. And there are lots of state functions in chemistry, but it's a state function which says that it doesn't matter how you get there. What matters is the state at the beginning and the state at the end of the process, and that's what matters. So you don't really have to know that's a state function. I'm just kind of giving that information to you. But we can use Hess's law to do lots of things that ordinarily in the laboratory would be very difficult to do or even impossible. We can use Hess's law to find the enthalpy changes for reactions that we actually can't do. And so let's look at an example. So here's a reaction. Reactant A goes to product B. And I'm asking you for the enthalpy change of reaction. So that's a little R right there. You saw that we had the enthalpy change of combustion was a C, enthalpy change of neutralization was an N. Now we have enthalpy change of reaction. So what is the enthalpy change between A to D? And so if we kind of go back earlier, if we have, say it's an endothermic reaction, what this question is, what's that enthalpy change? That's the delta H sub R that we're talking about here. What's the enthalpy change of reaction? Now, let's say that this experiment is actually impossible to do in the lab, or for some reason we don't want to do it. We can figure out this with other data. And so here's how we're going to apply Hess's law. Hess's law says that we can, if you sum up reactions, the total enthalpy change is equal to the enthalpy of the individual the total reaction. So we need to use these three reactions. So we have three different chemical reactions, and we need to produce out of these three A turning into D. And so you just kind of have to do some problem solving here and figure it out. But we know that we want A on the left side. And so we're going to go down here, we're going to find a reaction that has A on the left side. And that is this particular reaction. A forms B. And the enthalpy change for that is negative 150. Okay, we want D on the right side. In these reactions, we don't have any D's on the right side, but we do have a D on the left side here. And so if we flip this reaction, and instead of making D go to C, we make C go to D, that will give us D on the right side. Now, when you flip a reaction, you flip the sign of the enthalpy. So if this is endothermic, D goes to C as endothermic. C going to D would be exothermic, so that sign flips. So there's that enthalpy. And so we have our A and our D that we want to have, but we have this C and this B, and we've got to get rid of C and B somehow. So we're going to use this reaction to get rid of C and B. Now if I put C on the left side, that's going to give me two C's. So if I flip this reaction, flip that reaction around and make it B going to C, once again that means I flip my sign here, so that's negative 280. Now what happens is if I add these reactions up, The B here cancels the B there because they're on opposite sides of the reaction. The C here cancels the C here, and I end up with A going to D. That's my sum reaction. A goes to D. And the enthalpy change of that reaction is going to be the sum, the addition of these three enthalpies. So if we add those enthalpies up, then we'll get the answer. And that would be negative 630 would be our enthalpy change of reaction. So that's Hess's law. Hess's law says we can sum up reactions, and the overall reaction is equal to the sum of the individual reactions. The pathway of how we got to A to D doesn't matter. How we get from A to D doesn't matter. If we can cancel all this stuff out, we get the overall enthalpy change. So let's do a real example. I'm going to take solid carbon plus 2 hydrogens to make methane. So that's the reaction, and I want to know what is the delta H of reaction to produce this. What's the enthalpy of reaction? And so I am given some data to solve this problem. So here's the data that I'm given. So here are 3 experiments. Now if I can somehow manipulate these 3 experiments to produce this reaction, then all I have to do is add up the enthalpies, and I'll have the enthalpy of reaction for this reaction. And so looking at what I have carbon on the left in the solid form. So I need to find carbon in one of these reactions on the left, and if it's not on the left, flip the reaction and write that down. And so here we go. We got it right there. And so C solid plus O2 makes CO2. And my enthalpy for that is negative 393.5. Okay, so I'm good for that. I need CH4 on the right. And so let's find CH4 down here. It's right here. So it's on the wrong side, so I'm going to have to flip this reaction over. And so if I flip it, I'm going to have CO2 plus 2H2O making CH4 plus 2O2. And when I flip this reaction, I have to flip the sign of the enthalpy, so that becomes positive 890.3. Okay, so I've got my C on the left. So I want that. I've got my CH4 on the right. I want that. I need to have hydrogens on the left, and I got a whole bunch of other stuff down here I need to get rid of. And so I'm going to use this last equation to try and figure out how to get rid of stuff. And so actually the CO2s that are here are already going to cancel each other out. And I've got 2 oxygens canceling, or 1 oxygen here canceling 1 oxygen there. So I have 1 oxygen left over there. So I need to get rid of some water. I've got 2 waters here. In this equation I have water, but I only have 1 water here. So I need to multiply. I need to get 2 water. So I need to times this equation by 2. And so that's going to give me 2H2 plus 2 times a half is going to be an oxygen and 2 waters. And so I'm going to multiply this by 2, because whatever I do to the equation, I got to do it to the enthalpy sign. So that's going to be 2 times negative 285.8. Okay. Now looking again at our summation, now I've got my 2 waters canceling my 2 waters. My last oxygen here is going to get canceled there, and now I've got my 2 hydrogens. So I've got my C on the left side. Here's my arrows. On the left side I've got my C, I've got my 2 hydrogens, and on the right side everything cancels out except for my CH4. So I have, using these 3 equations, I've summed them up. I'm going to take my values, they're kind of mixed in here, so I'll take that enthalpy, and that enthalpy, and I'm going to add those 3 together, and that will give me my enthalpy of this reaction.